Hello, I'm Mr. Bob, and welcome to my Algebra 1 review series. This video covers Chapter 1, Section 3, titled Exploring Real Numbers. By the end of this video, you will have reviewed methods for classifying numbers and comparing numbers. This includes reviewing the classification of numbers, comparing numbers, ordering numbers, and finding absolute values of numbers. Additionally, along the way, you will review a real-world problem involving whole and rational numbers. If you would like me to cover any of the topics here in greater detail, please leave your request in the comment section below. Please subscribe to the channel if you find this video to be helpful. Thank you. Okay, before we get started with the review, I want to touch on a few definitions. Natural numbers. The natural numbers are 1, 2, 3, 4, 5, and on and on and on and on. They come from the early days when numbers were just being invented, if you will. And people would talk to each other. They say, well, how many do you have? I said, 1, 2, 3, 4. The concept of zero in the very early days didn't exist, of actually thinking I have nothing as a number. Then whole numbers were created. And that what they did is they took the natural numbers and added zero to it. So then you could get down to zero and start counting from there. Integers are whole numbers with the addition of all the negative numbers. So you had 0, 1, 2, 3, 4, 5, but now you have -1, -2, negative, and they both go on forever in both directions. Those are integers. Rational numbers. A rational number is any number that you can write in the form of a divided by b, where a and b are integers, and a is not, and then b is not equal to 0. Can't have 0 as a divisor. So, but you 1/3, 1/3, 5/10, doesn't matter. -2/7, they're all rational numbers. And those are all integers that I was counting out there. Irrational numbers. An irrational number cannot be expressed as a divided by b, where a and b are both integers. Examples include 0.1010000100, on and on forever. Okay, you can't express that as like a divided by b to come up with that. Pi is another one. It's an infinite series of numbers, and you cannot express it in terms of two integers, one dividing into the other one. The square root of 10 is not possible to be defined by two integers, the division of two integers. Real numbers, on the other hand, now, together, rational numbers and irrational numbers form the set of all real numbers. So rational numbers, the ones that we were talking about that you could form from a divided by b, and all the irrational numbers, the ones that you cannot express by a divided by b, right? All of those together are what we call real numbers. Then a counter example. Any statement that proves a statement false is a counter example. Inequality. An inequality is a mathematical sentence that compares the value of two expressions using an inequality symbol such as less than or greater than. Opposites. Two numbers that are on the same distance from 0 on the number line but lie in opposite directions are opposites. Like -1 and 1. -21 and 21. Those are opposites. Same distance from 0, but in opposite directions. And then finally, an absolute value. Absolute value of a number is its distance from 0 on the number line. So a -3 is 3 units from 0, just like 3 is 3 units from 0. But the absolute value of -3 is that distance without a negative sign. It's just how far is it? It's 3 units away. Okay? Okay, objective 1, classifying numbers. Each of the graphs below show a set of numbers on a number line. The number below the point is its coordinate on the number line. So we're going to look at the red points. And you notice that we're talking about the number beneath those points are the coordinate. So natural numbers, 1, 2, 3, 4, 5, whatever, and indefinitely. On the number line, you see is 1 right here is the point 1, 1, 2, 3, Okay, that's the coordinate point right there, 1, 2, and 3 on the number line. Whole numbers have added 0 to it. So now we've got 0, 1, 2, 3, and on and on and on. Integers have added the negative half, or the negative piece to this whole scheme of numbers. So we have 0, 1, 2, 3, 4, but you have also -1, -2, -3, -4, forever. And you see all these points are found on the number line. Conveniently, they're all integers. Right here, these bottom row, and they're all on the number line. Okay, as you can see, the set of integers has negative numbers as well as 0 and positive numbers. There are also numbers that are not integers, such as 0.37 or 1/2, which are rational numbers. A rational number is any number that you can write in the form of a divided by b, where a and b are integers and b is not equal to 0. A rational number in decimal form is either terminating, such as 6.27, or repeating, such as 8.22222 forever. But you could also write that 8.22222 as 8.2 with a line over the top of it. Whatever the line is above, it says that piece repeats. If I'll draw a little example on here, if your number was 7.21212121 and it repeats like that forever, you could write that as 7.21 and put the line over both of them. I should clean that up a little bit. It looks like a 5, sorry. And put the line, and make a red line over it, and put the line above both of them. If it were 3, if it was 7.2159, 7.2159, 7.2159, you'd put it 7.2159 and put the line over the entire piece. And that means this from now on is the way it repeats. So this bottom one right here says this is 7.21212121. All integers are rational numbers because you can write any integer, n, as that integer, as n divided by 1. So now it's a rational number. Because rational numbers, as we just said, is any number that you can define as a divided by b, where a and b are both integers. So that makes all your integers rational numbers also. So continuing on with our objective 1, you may need to determine a set of numbers that is reasonable for a given situation. For example, suppose you have 110 students, 110 students are going on a field trip. Each bus that's going to take these students can hold 40 students. Find the number of buses needed. So what do? We divide 110 by 40. Okay, the answer is rational number 2.75 buses. 2.75. However, it's not a whole number of buses. What do you need? You need whole buses. You would read a whole number of buses, or 3, right? You would need a whole number of bus. So then you could carry 120 students, but you still need that third bus. So that's a little part to this. Okay, objective 1 continued here. An irrational number cannot be expressed in the form of a divided by b, where a and b are integers. Here are 3 irrational numbers: 0.101001001000. Well, from then on and on and on, we don't know what the numbers are, but they don't repeat and they continue forever. Pi, the pi is 3.1415, whatever, 159, I think. It doesn't go on. It goes on forever. It doesn't repeat. It's irrational. It cannot be described as one integer divided by another integer. Square root of 10. If you take the square root of 10, you have to use your calculator, and it's going to be some number that's going to be an infinite number long. Something point, something, 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 on forever, non-repeating. So together, rational numbers and irrational numbers form a set of real numbers. The Venn diagram here shows relationships of the sets of numbers that make up the set of real numbers. Okay. So what do we have here? If we look on the left-hand side, we have rational numbers. And rational numbers, starting on the inside, start with the whole numbers. You can go even further and do natural numbers way in and just get rid of the zero here. Okay. And then you'd have basically the natural numbers. But you wouldn't be talking about square roots and stuff. They didn't have them probably back then, but still. Then we had whole numbers. We added the zero to all the natural numbers. Then integers came along. That's got the negative values in here. Okay. And then finally there's rational numbers. That's all the rest of them. 0.75, negative 2/3, 5/8, 0.37, 1/2, 0.31 repeating. See the little repeating sign right there? Repeating. Now on the other side, we have the irrational numbers, which is the ones we spoke about. The square root of 10, pi. Here's pi right here. Here's this 0, 1, 0, 1, 1, or 0, 0.10, 0.11. Oh, whatever, you see it. 0.1010001000, something, something. We also have the square root of 2/3 and the square root of 1.6. How about negative the square root of 123? Those are all irrational numbers. But this forms the set of what? All of these, all combined, form the set of real numbers. Those are our real numbers. So continuing objective 1, suppose a friend says that all integers are whole numbers. And you respond that, well, negative 3 is an integer, but it's not a whole number. You are using a counterexample to prove a statement is false. Any example that proves a statement is false is a counterexample. You need only one counterexample to prove that the statement is false, while a proof to show that a statement is true may be more complicated. You might have multiple steps. You have to look at it, maybe your proof from multiple different angles to make sure that what you're saying is true. Example 1, classifying numbers. Name the set or sets of numbers to which each number belongs. So the first number, negative 17 over 31, negative 17/31. That's a rational number. It's rational, okay? So 20b, 23. 23 is a natural number. It's a whole number. It's an integer, and it's a rational number because 23 divided by 1 makes it rational. Okay, it can be written as a fraction. 0, whole numbers, integers, rational numbers. 0 can be written as 0 divided by 1. It's a whole number. It's not a natural number because natural numbers didn't include 0. But whole numbers and natural numbers are exactly the same except for the inclusion of 0 in the whole numbers. That's why this is a whole number. And how about in D, 4.581? Well, that's rational numbers. Why? Because you can write 4,581 divided by 1,000. That's 2 integers. And it makes it a rational number. And then the answer, of course, is 4.581. Okay, example 1, check your understanding. I think you know now that I like you to stop the video and give this a try them out, see what you come up with. And then when you come back, we'll work on them together. So why don't you go ahead and stop the video and I'll wait. Okay, I'm assuming you've stopped and done the work and come back. So let's go over it. Name the set or sets of numbers to which each number belongs, just like the previous slide. Negative 12. Well, what sets does negative 12 belong to? It's not a whole number. It's not a natural number, right? Because it's a negative number. So a negative number is an integer, and any integer is also a rational number. So it's integers, integer, and rational. Okay? How about B? 5/12. Well, is it an integer? No. It's not a whole number. It's not a natural number. but it is a rational number because it can be defined as 5 divided by 12, and both of those are integers. How about C, negative 4.67? Well, it's a rational number. It's not an integer because it's 4.67, right? It's rational because it can be defined as 467 divided by 100, and it's negative, so it makes it on the negative side, but it's a rational number. And then how about 6? Well, 6 happens to be all of them, doesn't it? Because it's a natural number. It's a whole number, right? Because it included, it doesn't need to worry about 0. It doesn't worry about the negative numbers. So it is an integer, and it's rational. Why is it rational? Because it can be written as 6 divided by 1. Okay? Okay, example 2. It's your real world problem. Okay? So it says, which set of numbers is most reasonable for each situation? So you could pick a number, which most reasonable set of numbers to use if you're going to try to calculate these questions here, resolve these questions. So it says A, it says the number of students who will go on a class trip. Well, is it natural numbers? 1, 2, 3, 4, 5, 6? Well, it sounds like it is, right? But guess what? You could also have whole numbers. Why? Because you could have 0 students going on the trip, but you can't have negative. It can't be an integer because you can't have negative students going on the trip. So this one's going to be whole numbers. Okay. And how about the height of a door frame in your classroom or in your house or wherever the door frame is? The height. Should that be an integer? Should it be a whole number, a natural number? Or perhaps it's going to be something like 6 feet, 8 inches or 6.75 inches or whatever the case might be, right? So this is a rational number, right? Because it can be defined as 675 divided by 100. And I don't know what the door would be, but it's 6 feet 8 inches, right? Is usually what we think of. So, and 0.8 is 2/3 of a foot. So I guess it would be 6.6. There it is. It's going to be 6.666 forever. So that'd be repeating. So I could write it this way. We learned it, right? I could say 6.6 repeating. Okay. I'll go ahead and make this look a little nicer. I'll erase this. Okay. So, example 2, check your understanding. It's your turn to give us a try. This is just like the previous slide. Directions. Which set of number is most reasonable for the cost of a scooter? A motor scooter, I think is what they're talking about here. So go ahead and stop the video, think about it, come on back, answer the question. We'll do it together. Okay, I'm sure you've stopped it and done this by now. So I think this cost of a scooter could be $485.22, right? So it's probably not going to be an even integer. It's not going to be negative money. They're not going to give you money to take the scooter. It could be 0 if someone gives it to you for free, but it's probably going to be a rational number because it's going to be some fractional amount of dollars or whatever the case might be. So I'm going to say in your case, it's going to be rational. Okay. Okay, in this example, example 3, we're going to be using counter examples. So let's try. So in each statement, it says, is each statement true or false? If it's false, give a counter example. Okay. All whole numbers are rational numbers. All whole numbers are rational numbers. Okay. Well, it says every whole number can be written in the form of n over 1. And that's the definition of a rational number. So all whole numbers are rational numbers. The statement is true. How about the square of a number is always greater than the number. So remember, we're trying to decide, is this true what the statement is? Is it true or false? The square of a number is always greater than the number. Is that true or false? Well, the square of 0.5 is 0.25, and 0.25 is not greater than 0.5. So the statement is false. That's your counter example. Well, 0.25 or whatever your number might be, but less than 0.5, right? Okay, example 3, check your understanding. It's your turn. Is each statement true or false? And if it's false, give a counter example. I'll read them to you. All whole numbers are integers. And B, no fractions are whole numbers. So why don't you go ahead and take some time and look at this, and then when you come back, we'll try it together. Okay, so I'm assuming you stopped the video, you wrote down your answers, and now we're going to look at them together. So, is each statement true or false? If it's false, give a counter example. Problem A, all whole numbers are integers. That is true. They are all integers. So all integers are not all whole numbers, right? But all whole numbers are integers. So B, no fractions are whole numbers. Well, this is false because I can show you a fraction. We can say, right, so this one, first one is true. This one here is false. And why? Because I can give you a no. I can say here, how about 3? Okay, there's a whole number. Can I write it as a fraction? Yes, 3 divided by 1. That's a fraction. So there's a fraction. And it says no whole numbers are fractions. Well, it's false because here's a whole number and it's a fraction. So there we go. Objective 2A. There's going to be a couple sheets here for this one. Comparing numbers. An inequality is a mathematical sentence that compares two values of two expressions using an inequality symbol such as less than or greater than. When you compare two real numbers, only one of these can be true. And they're showing you 3 examples. A can either be less than B, A can be less than, or A can be equal to B, or A can be greater than B. Those are the only possibilities in terms of comparisons. When you compare two real numbers, only one of these can be true. Okay. There are 3 other symbols rather, that compare two values. And they are A is less than or equal to B, A is not equal to B, or A is greater than or equal to B. So those are the other options, but as you notice, in the greater than, they just added the equal, and that adds the part, the equal in the middle. Or you can say that it's not equal. So that would be A is greater than B or A is less than B. So that's the not equal part. So the number line below shows how values of numbers increase as you go to the right on the number line. So as we're looking at number lines, think of it this way, that the numbers are always getting larger when you're going to the right, and they're getting smaller. So kind of look at this. This is important because it sometimes troubles students when they're trying to imagine this in their head, this number line with numbers larger than or whatever, okay? So we're going to look at the number. It goes from 0, right here is 0. There's 0, and it goes -1 right here and +1 right here. So everybody can say, well, obviously -1 is less than +1. And we went to the right from -1 to 0 to +1. We're moving to the right, and things are getting larger. The values are larger. Okay, so now when we look at the negative numbers, is -1 larger than -2? The answer to that is yes. How about this? Let's look at these fractions. Negative fractions. What's larger, a -1/2 or -1/8? Well, you think, oh, -1/2 is a larger number. Well, larger numbers go to the right. They don't go to the left. So 1/2 is smaller than -1/2 is smaller than -1/8. let's look at the statement here. It says negative 1/8 is to the right of negative 1/2. So negative 1/8 is greater than negative 1/2. And negative 1/2 is less than negative 1/8. So even though the number looks like it's bigger because it says a half, that's bigger than an eighth, but since it's on the negative side, actually the numbers going to the left are getting smaller. The quantity, if you will, think of it that way. To compare fractions, you may find it helpful to write the fractions as decimals. Sometimes it's easier to see it that way too, but then you can compare the decimals. Okay? So example 4, ordering the fractions. So based on what we just learned, let's write negative 3/8, negative 1/2, and negative 5/12 in order from least to greatest. Least to greatest. Least is on the left, greatest is going to the right, right? So negative 3/8 is equal to, well, so what we're doing also is we're going to write them in decimal form because it suggested that on the previous slide. So negative 3/8 is equal to negative 0.375. So it says start by writing each as a fraction, each fraction as a decimal. Negative 1/2 is negative 0.5, and negative 5 divided by 12, or 5/12, is negative 0.4166. Or here's our repeating symbol again. This is interesting because it's helping us here. Negative 0.416 repeating because it starts repeating at the sixes. So now put them in order. What is the largest and which is the smallest? Well, the smallest number is the negative 0.5. And because it's, since you can see that the negative 0.5 appears to be larger than the negative 0.4 and larger than the negative 0.3, but we know that the farther the number is to the left, the smaller the value. So here, negative 5 is less than negative 0.41666 continuously, and that's less than negative 0.375. So the decimals ordered from least, last to greatest, right? Least to greatest. Okay, from least to greatest, the fractions are negative 1/2, negative 5/12, and then negative 3/8. Okay, example 4, slide A, because there's going to be another slide after this. Check your understanding. So you can stop the video and do it on your own and see what you come back with. I'll wait for you. I'll read it to you first. It says write 1/12, negative 2/3, and negative 5/8 in order from least to greatest. I'll wait. Okay, so I assume you've done that. So let's take a look at them. First, I wrote them as decimals. So negative 2/3 is equal to negative 0.66666 forever. Negative 5/8 is equal to negative 0.625. That's a terminating, right? And then finally, 1 divided by 12, or 1/12, is equal to 0.083. And it's going to be 833333 forever. So we could also write that then as we could have written this one. I'll give an example here by writing it. I could have wrote it as negative 0.6 repeating. This one here, I could have written as 0.083 repeating. Okay, so let's put them in order. So what is the smallest number? Well, the smallest number on the smallest negative number is the one that's numerically appears to be the largest. So we have 0.66666 and we have 625. Well, 66 is numerically is greater than 625. So the first one we're going to have down here is going to be negative. So this is the least. Negative 0.6 repeating. Then we have the negative 5/8. That's just naturally going to come next because they're negative 0.625. And then finally we have the positive number, which is 0.083 repeating. And so in order by the fractions, it's the 666 is the negative 2/3, negative 2/3, and then it's the negative 5/8, and comma, then finally 1/12. Okay, good. Okay, example 5, finding absolute value. Two numbers that are the same distance from 0 on the number line, but lie in opposite directions are opposites, right? So here, let's look at the number line. So we start here at 0. We're starting at 0, negative 3 and 3. They lie the same distance from 0, 3 units from 0, right? Negative 3 and 3 are the same distance from 0, so negative 3 and 3 are opposites, okay? So the absolute value of a number is its distance from 0 on the number line. Both negative 3 and positive 3 are 3 units away from 0. Both have an absolute value of 3. The distance is the absolute value. You can't have a negative distance if you think of it in distance, right? You can't say, well, I'm going to go backwards in space or whatever. You only go forward in distance, right? So anyways, so this is, you write the absolute value of negative 3 as the absolute value sign, negative 3, and then another absolute value. These are pipes on the keyboard. We call them pipes, but it's just part of the absolute value symbol. It's 2 vertical lines. So find each absolute value. Problem A, the absolute value of 12 is 12. 12 is 12 units from 0 on the number line. So the absolute value of 12 is 12. How about the absolute value for B, the absolute value of negative 2/3? Okay, negative 2/3 is 2/3 units from 0 on the number line. So the absolute value of negative 2/3 is equal to 2/3. It's the units, nothing to do with the direction. And finally, how about the absolute value of 0? Well, 0 is at the 0 point on the number line. And the absolute value of 0 is 0. Okay, so why don't you go ahead and try these on your own? Same kind of a thing. Stop the video, work them out, come on back, we'll do them together, right? Find each absolute value. I'll give you some time. Okay, I'm going to assume you've done that and you're back with me. So let's go through it. A, what is the absolute value of 5? The absolute value of 5 is 5. B, what is the absolute value of negative 4? Well, how many units is negative 4 from 0? It's 4 units. Its distance is 4 units from 0. How about what is the distance from 0 for the absolute value of negative 3.7? The absolute value of negative 3.7 from 0 is 3.7. And how about finally D? The absolute value of 5 divided by 7, 5/7, is what? Well, what's the distance 5/7 is from 0 on the number line? It is 5/7. Okay?